All right, let's see what we can do. We need to eliminate this lambda production. All right, so we need to get rid of what would happen with the lambda there. So what happens to S if A becomes lambda? If A becomes lambda, S could become BA. Or it could become, well, let's keep the one that it could have already been, right? It still could have been ABA. Let's keep that. Then it could become BA, or it could become AB, or if both A's were eventually replaced with lambda, it could become just B. Does that make sense? What happens with A? A could still be the AA that it was before, or if A is lambda, if we replace it with lambda, A would become the little a. Does that make sense? So that was the idea of where these pieces over here came from, right? The x could be replaced with lambda, so we could have had each one of those pieces, ax, then b without the x at the end, a with bx, or just ab. All right, so this is step one. We've eliminated the lambda production. All right, what about eliminate variable unit productions? Well, there aren't any, right? There's nothing that, like wherever it was, I guess we erased it. There's nothing that has one variable being able to be replaced with a single other variable. So we skip step two. All right, we need to eliminate long productions. Are there any long productions to eliminate? There's this one that we need to eliminate. All right, so what could we do? We need another variable, x. All right, so we have another variable x, and what does it have to take on? It has to take on part of what's happening right here. So maybe we let x be AB. But if we let x be AB, what happens here? This becomes XA. Okay, so we've eliminated, and that's the only long production that we have, so we've eliminated that. All right, now what do we need to do? Now we need to move all the terminals to unit productions. So how do we move terminals to unit productions? Well, things like this can't stand. So maybe we replace b with little b.
Wouldn't AB also become x?
No, we don't want it to become x because we want to work toward creating two variables.
Right.
This is x, but that brings us back around to creating a unit. So we want to avoid going back up to create a new unit terminal or a new unit production. All right, so if we let b represent b and maybe c transition to c, what happens? BA in this production now becomes what? The variable b, a. AB becomes a followed by the variable b. So we've created these binary replacements. And here, what happens? That becomes AC, and X becomes AB. And so a short, small grammar that only had 3 productions becomes much longer. But again, the nice part about that much longer grammar is that now all derivation trees are binary trees, and we're going to use that in the next step. Does that make sense? So this grammar was created by going through those 4 steps. This grammar, again, in Chomsky normal form, created from here. So if we have a grammar that doesn't include the empty string, if the language does not include the empty string, then we can go through this process to convert. Now, well, what happens if it does include the empty string? Then we can't eliminate that lambda production, right? Because one of those lambda productions has to still be there somewhere, somehow. And since step 1 is eliminate the production, the lambda productions, we can't get past that step. Okay, so what happens if your language does include that? Then again, maybe we deal with the empty string separately. Right? So we look at deal with the empty string as a special case. Everything else we can deal with in this way. All right, so what happens if we have everything in this format? If we have everything in Chomsky normal form, when you start somewhere, we're going to be able to produce some strings, right? The strings of the language from that starting position. What's going to happen as we work through, if our string that we're deriving is long enough, and our derivation tree is a binary tree, what's going to happen? There's going to be some variable that we use twice. Right? The string's long enough and you only have, it's binary. There's going to have to be some variable that gets used twice. Maybe more than twice, but at least twice. Does that make sense? This is like the automaton. If the string's long enough, there's some state you have to come back to. You have a finite number of variables and a really long string. So your derivation eventually, if the string is long enough, will have to reuse a variable. So what happens? From here, we derive some string that uses this variable multiple times. From this first, or this particular location, we can derive these strings. Something, right? Something that fits in here. And from here, we can derive whatever we derive directly, like the last time that we use t. So what we're going to get is a string that's in 5 different pieces. Right? This part that doesn't involve t, some other part over here at the end that doesn't involve that variable t, and then this part in the middle that involves using t here and then potentially using t again later.
Is this somehow related to the, I can't think of what it's called, but it's the pyramid. It starts with 1, then it goes 1, 1.
Oh, no. So like Pascal's triangle?
Yeah, Pascal's triangle.
No. I think we can probably connect everything in some way to Pascal's triangle, but I don't know of a way directly. This is just so happens to have the same kind of triangular shape.
That's what it seems like. It's the first thing that popped in my head.
All right, so here's what happens. If our string that we're generating is long enough, then this kind of thing has to happen. And not only does this have to happen, we have some conditions. So if we have a context-free language and a long enough string, we'll let our string, think of our string, can be written in this way, where the Vx part is non-empty. The VWX part, the length of it, is something less than or equal to some particular number k. So this part's not too long because we eventually terminate. And then the last part is that if we can generate something like this, what happens if we were to repeat the t portion in here? What will happen is we will be able to create as many copies of this as we want. What happens if we skip this particular derivation, right? This particular choice that led to VWX. If we skip that, that would lead to UWX, right? Skip this one, leads to UWX.
Or could it be UWY?
I'm sorry, yes, UWY is what I meant. Thank you.
Okay, sorry.
I pointed at it, but I saw the X out of the corner of my eye. I apologize. Yes, if we don't use that particular derivation, then the string that we get rather than UVWXY is we can also derive the string UWY.
And then any t beyond that just increases the amount of v's and x's.
Yeah. So what would happen if instead here instead of replacing t with w, what if I replace t with this thing again? I get another copy, right? I would have VWX, but the W I replace with VWX again.
Yep. So it's squaring the v and x consistently every time.
Well, so what would happen if I didn't quite get here yet? I did it one more time.
But it would be v, v, v. It's increasing the exponent number.
Yeah. So what's going to happen? We're going to get equal copies of v and x. Right? So what will happen is that u, v to the I, w, x to the I, y.
And then it's I however many iterations of t exist.
I greater than or equal to 0. Will also be in the language. And so if we have a context-free grammar and a string that's long enough, then that string, well, if the string is long enough, then there's some variable that's going to be repeated.
Now, is that for all context-free grammars or
Yes.
are ones that we've been able to...
Well, so it's true for all context-free grammars, but to prove that you can do it, it's convert it to Chomsky normal form.
Okay.
And, well, converting it to Chomsky normal form tells you how long the string needs to be.
Okay.
So this is true for all grammars because you will eventually have to reuse a variable. And what we really focus on in all of this is actually in the derivation of the string, the last variable that got reused, rather than in the other pumping lemma, it was the first state that got revisited. We're actually going to look at the last variable that gets reused.
Okay.
So what happens? I derive my string in this way.
No.
When I derived this string, I'm now looking at what other strings could I derive. And I could say, well, let's just skip this last one. And that gives us let's skip this one, right? Let's skip the next to last one. When I get here, instead of going VWX like we said there, we could have just gone W. Or we could say, well, when we get here, instead of replacing with W, let's replace it with this again. and again and again. And so we're able to generate pieces like this. So your question, I'm sorry?
Yes. My question was, you said it was the last variable that is repeated. So does that mean if there's a variable before this, say like A, that is repeated, since it came before this one, and this one is the after one, we reference this variable?
Yeah, so all we're saying here is that you can do it.
Yeah.
And so we're kind of looking at, well, what was the last variable before termination, before we got to the string we were trying to get to?
Okay.
The last one that got repeated. There might have been other variables in between, but they didn't get repeated.
Yeah.
And it's just so that we can say, yes, this will happen, and this is what happens, this is what you can do. You can make it work with other parts, but this is just kind of the proof that it, or at least the idea, the concept of a proof, that this will always happen. There will always be some place that the repetition happens. And so if we just replace this t with another copy of that, or if we decide, well, let's from here, let's just go ahead and terminate. So that would get rid of the v and x, the other part would give us those duplications like that. And you can do this as many times as you like and generate new strings that are in the language. So what do we have here? We have that if the language is context-free, then you can do this. We can break a long enough string up in this way where these things happen. So what happens if you find a string where you can't do this? You find a string in a language and you can't do this, that means that it's not a context-free language, right? So this is our pumping lemma for context-free languages. Works just like the pumping lemma that we had before. Because what happens in a regular language? In a regular language, there's a certain amount of repetition. There's a certain pattern to things. In a context-free language, there's also a certain amount of repetition. It's just that the repetition's a little more involved, but the idea is the same. So before our pumping lemma, we looked at the automaton for that. For this, for the regular language, we looked at the automaton rather than the regular expressions. For here, rather than looking at the PDA, we're looking at the grammar. And so how long is long enough? Well, this comes back to the, okay, put things in Chomsky normal form. In Chomsky normal form, you will have this binary tree. And it turns out that long enough is something like 2 to the number of variables in Chomsky normal form plus 1. So if your string is longer than that, then you are repeating some variable, right? That's because the binary tree, if you have this many variables, you can create 2 to that many leaves for the tree. So if you have one more thing to generate that, you have to reuse one of the variables that you already had. All right, so these might be very, very long strings before this kicks in. Before, the idea was we just had to have a string that was at least as long as the number of states in our machine. Now what happens, we might have to have really, really long strings relative to the number of variables. But if the string is long enough, there will be repetition, can't be avoided, and then we can pump things up or down to create new strings in our language. All right, we're not going to completely go through the proof, but the idea, but we will use it for a couple of examples. All right, so sort of kind of make sense?
Yep.
All right, so how do we use it? We use it in the same kind of way. We say, here's a language that we think might be, here's a language we think that might be context-free, or actually, here's a language we think might not be context-free. How do we prove that it's not context-free? Pick a string and show that if you try to pump that in this way, that you get something that doesn't fit the pattern.
Okay.
All right?
So it's just a way to prove that strings that are given are within a context-free grammar.
It's a way to prove that a particular language is not context free. Right? It's like the pumping lemma before, where you could use it to prove that a language was not regular, because you find a string that's long enough but can't be pumped. If you pump it, you break the pattern.
And if it's not context free, that also means it's not regular, correct?
Yes, because regular is a subset of context free.
Yes.
So so we had the regular languages, and then we had the context free languages. So if it's not inside the bigger circle, it's definitely not inside the smaller circle.
Now, if it's not inside the smaller circle, if it's not a regular language, it could still be a context free.
Yes, we have seen palindromes and the equal number of zeros and ones and lots of languages that are out here.
So that's a big differentiation between them.
So then what happens, there are other languages that are out here.
Of course.
All right? So, and this is how we can prove that there are languages outside that. All right, so let's pick an example of a language, and let's see whether we think it's context free. Remember, again, we haven't proved this, but that context free language, there will be a context free grammar for it or a push down automaton for it, right? And that these two, we kind of talked about how they're equivalent. We haven't formally proved that. But a context-free language has a context-free grammar, and it also has a push-down automaton. So we can describe one or the other way of solving the problem in this case. All right, so let's look at this language. Is this language context-free?
Pick some strings and figure it out.
I'm going to see if we can generate strings, either building a grammar for it, or can we describe a push-down automaton?